Comparatively, as Nicholas Copernicus introduced the heliocentric model, one more stunning rectification of how we could decipher the universe could emerge, beginning a conversation known as the rise of cosmology. This rise is marked by fundamental incongruities in our assessments and understanding of the universe's crucial properties, like its age, size, and speed of evolution. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope JWST has intensified this conversation with findings that challenge the laws of physics. So, what exactly is this crisis, and how does the James Webb Space Telescope contribute to it? Well, contributing might be a bit of a misnomer. It's more like a review that has been in progress. The crisis refers to how our understanding of the universe is tested, particularly concerning its age and size, which are connected by a broad safety margin. The introduction of the JWST has been crucial here. Before this advancement, we were limited in how far we could see into the early universe. However, with the JWST's advanced capabilities, space scientists can explore much more distant galaxies, providing new perspectives on the universe and challenging some of our previous assumptions. This progress allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming, providing essential data that can either support or challenge our current models of the universe. To understand the crisis in detail, examining context is crucial. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter, lambda CDM model, has been remarkably successful in explaining various aspects of the universe, from gravitational lensing to the structure of the cosmic web and the development of galaxies. The lambda CDM model suggests that the universe began with a massive explosion, followed by a period of rapid expansion, and has been expanding ever since. It includes components like dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each critical observation, especially with advanced instruments like the JWST, raises the possibility that our current model may be incomplete or needs updating. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages of the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less developed, and contain fewer heavy elements compared to those in the nearby universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time. According to this model, galaxies should be smaller, bluer, less developed, and poorer in heavy elements at greater galactic distances. This would lead us to expect to observe periods of the universe without obvious stars or galaxies. However, researchers have found inconsistent evidence that challenges these expectations, resulting in a crisis in cosmology. This crisis centers on the uncertainty about the age of the universe. Different measurement methods yield different results, leaving cosmologists struggling to reconcile these discrepancies. To address this issue, scientists use several techniques to measure the age of the universe. One of them involves studying cosmic background radiation, which involves decoding the history of the universe's expansion and using mathematical models like the Friedmann equations based on Einstein's theory of general relativity. These calculations help determine the expansion rate and thus the universe's age. The cosmic microwave background CMB, a remnant radiation from the early universe, is a critical tool for this calculation. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable information about the universe's composition. Another approach involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles because they have a known intrinsic brightness. By comparing their known luminosity with their observed brightness, astronomers can determine their distance and, consequently, the universe's expansion rate at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now essential for cosmological calculations. It is particularly useful for determining the Hubble constant, a measure of the universe's expansion rate. Although not truly constant, The Hubble constant is instrumental in charting the universe's growth since the Big Bang, approximately 13.8 billion years ago. NASA has observed that the implications of this expansion rate are significant. If the expansion is slowing, it suggests the presence of an unknown force, perhaps dark matter, influencing the process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and impact of dark energy. In January 2018, scientists discovered something intriguing. Different telescopes showed varying expansion rates depending on the observation point. The Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower rate in more distant parts of the universe. This discrepancy underscores the universe's vastness and reminds us of Edwin Hubble's pioneering work in 1929, which first proposed the universe's expansion. Technological advances, such as the Hubble and Gaia telescopes, have allowed more refined measurements. Different telescopes use CMB readings to calculate the Hubble constant, though this method has limitations due to the availability of supernovae for distant observations. Since the discovery of dark energy in the 20th century, scientists have been puzzled by the inconsistencies between different approaches to measuring the universe's age and expansion rate. As measurement technology becomes more precise, smaller variations emerge, driven by more advanced systems. Although the differences are minor, only 10 to 20 million years in a universe about 13.77 billion years old, they still warrant careful examination. One potential explanation for this discrepancy could be flaws in our CMB measurements. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it might fluctuate over time or be connected to dark energy or some other unknown factor. This has led to various experimental studies. The accuracy of supernova measurements is also questioned due to the complexity of star explosions, which can introduce uncertainties. Resolving these uncertainties could help reconcile measurement differences. This crisis has been further exacerbated by the JWST's discoveries. According to Neil deGrasse Tyson, the JWST has found objects in the universe that challenge our current understanding, indicating that our scientific models might need a complete overhaul. The issue is that we have no clear starting point for this revision. Current JWST images reveal galaxies much older than predicted by standard cosmological models, suggesting our models need a significant update. This discovery points to a fundamental crisis in cosmology that may redefine our understanding of the universe. The James Webb Space Telescope's JWST observations have intensified the crisis by revealing galaxies and structures that appear far older and more developed than they should be, according to the Lambda CDM model. These findings suggest that either the universe formed stars and galaxies much earlier than expected, or that our theoretical frameworks are missing crucial components. This has sparked a wave of discussions in the scientific community about whether our current understanding of galaxy formation and evolution needs significant revision. Implications for cosmology. One of the most striking observations is that the distant galaxies observed by the JWST are larger, more complex, and richer in heavy elements than they should be, based on their redshift values. Redshift is used to estimate how far away galaxies are, and, consequently, how old they are. Higher redshift values correspond to earlier epochs in the universe's history. The fact that these ancient galaxies exhibit characteristics of much later stages of development suggests that galaxy formation processes may have occurred more rapidly than the Lambda CDM model predicts. These observations raise fundamental questions. Did star formation begin earlier than we thought? If so, what processes could have accelerated this timeline? Are there unknown mechanisms influencing the evolution of early galaxies? Could our understanding of dark matter and dark energy be incomplete? Some theories suggest that dark matter might interact with normal matter or energy in ways we haven't yet understood. The Hubble tension. A key aspect of this cosmological crisis is the so-called Hubble tension, a discrepancy between measurements of the universe's expansion rate using different methods. When astronomers measure the expansion rate using the cosmic microwave background, CMB, and the lambda CDM model, they get a different value than when using type Ia supernovae or other local measurements. The JWST's observations have deepened this mystery, suggesting that something fundamental might be missing from our models of the universe's structure and evolution, possible solutions, and future directions. To resolve this crisis, cosmologists are exploring several avenues. 1. Revising the standard model. Some scientists propose modifications to the lambda CDM model, such as introducing new physics that could explain the accelerated evolution of galaxies. This could involve changes to our understanding of dark matter, dark energy, or the properties of the early universe. 2. New physics beyond the standard model. There is speculation that unknown particles or forces might be at play. Some theories suggest interactions between dark matter and ordinary matter that could alter the course of cosmic evolution. 3. Improving measurement techniques. Continued advancements in observational technology, including the JWST and future space telescopes, will provide more data to refine our measurements and models. Cross-checking these observations with ground-based telescopes and other space missions will be crucial. The broader impact. The cosmological crisis has profound implications for our understanding of fundamental physics. If the current discrepancies cannot be resolved within the framework of the lambda CDM model, it could signal the need for a paradigm shift in cosmology, much like the transition from the geocentric to the heliocentric model. This would not only change our understanding of the universe's history and structure, but also influence other areas of physics, including particle physics and general relativity. Conclusion: the discoveries made by the James Webb Space Telescope have opened up a new frontier in cosmology, challenging long-held assumptions about the age, size, and evolution of the universe. While the crisis has raised more questions than it has answered, it also presents an exciting opportunity for scientific advancement. As our observational tools become more sophisticated and our theoretical models more refined, we may be on the cusp of a major breakthrough that could reshape our understanding of the cosmos.